Hmm. All right. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh, and good afternoon, everyone. Sorry, I'm a little bit late. Mm, you can hear me well, right?
Yes,
Yes.
doctor.
Okay. All right. Good. Okay. Let me start the recording. All right. Okay. All right. So, basically today we're going to be looking at another data structure. Okay. So last week we looked at one data structure called hash, and we found out that we can actually do search, insert, and maybe the delay is not really constant, but you can it can reach into constant time. Basically, you can do search, insert in constant time. Okay, so today we're going to be looking at another data structure, which is can be used as a dictionary as well. But maybe it is not as the running time complexity. Maybe it is not going to be as fast as hash, but if, like, let's say you do not know what are the input size, okay, so perhaps you can use it's better to use this data structure that we're going to be looking at today, which is the binary search tree. Okay, so if, like, let's say you know that you're going to have like maybe like 100 size of input, so it's better to actually use hash, because you know what is the size of your input. But if, like, let's say you have no idea what is the size of your input, then perhaps it is better for you to use the PST, even though that the running time complexity is a little bit slow, but it is much more easier to much more appropriate to actually use PST for that. Okay, so today we're going to be looking at this BST, which is the binary search tree. Um, I think in one of the tutorial we kind of like accidentally looked into this, which is when we do. If you remember this one question, not this one question, where we try to build uh, a tree of height 4, height 2, 3, 4, 5, 6. Remember that question? So, and if you remember, I mentioned that, like, for you to have, even though you have the same element in a set, but you can have a different height, three heights. So that question is actually it is more towards describing the binary search tree. Okay, so whereby, like, you may get a different height tree depending on the sequence of how the element is being inserted into the BST. All right, so today we're going to be looking at this binary search tree. Okay, where we're going to be looking at how we can do search in BST, insertion, as well as deletion. I don't think I'm going to be looking into Fibonacci heaps, but you can always, like, if you're interested, you can always follow through. Okay, about the Fibonacci heap. But today we're going to just be looking at the binary search tree. Okay, so all right. So basically, right? Um, so please do not get confused with binary search. Okay, so binary search is whereby you have an array, a sorted array, and then you try to do the binary search, whereby you find the middle part, and then try to recursively find the key. So binary search tree, this algorithm is using a tree structure to keep the data, as opposed to the binary search, whereby we are just using normal array. Okay, All right. So let's look at the introduction of binary BST, binary search tree. Okay, so binary search tree, as you can see from the name itself, okay, it is mostly used for you to do data search. Okay, whereby it supports operations such as finding a key, right? Finding the key, finding minimum, finding maximum, predecessor, successor, doing insert of data, okay, as well as delete. All right. So you can use the search tree as dictionary as well as priority queue. Okay, so as we have learned in hash as well, we can use hash as dictionary as a dictionary as well, whereby the running time capacity can is near to constant. All right, but then as I mentioned, the trade-off between, you know, like whether you want to choose the hash or the binary search tree is that if let's say the size of the input is unknown, perhaps it is better for you to use the binary search tree instead. Okay, because you know, like the operation of resizing the hash table will take additional running time for you to do that, right? Okay. So, and then when we talk about priority queue, I believe we have look at another implementation where another algorithm that we can implement the priority queue. Do you remember what is it, class? We've looked at one algorithm before where we can use that algorithm to implement the priority queue. Do you remember, class? Anyone? Yes? No? Remember we look into priority queue before, and we can sort of like extract max in constant time. Not extract max, but find what is the maximum in the maximum element in constant time. Class? Do you remember?
Mm, mm, no.
No, we don't. I think we learned this like 2 weeks ago before we look into hash. Nobody? Ah, remember we implement priority queue using another kind of tree, but we don't. It's not a binary search tree, but we implement the easier tree as well, a tree structure. Do you remember? Ah, no,
Sorry,
class.
doctor, but I can't see. No, sorry, doctor.
And whenever you don't remember, I always like remember myself. Okay, I'm not that old, you know, because like I still remember we learned this, like 2 weeks ago. Remember we look into heaps, the max heap, min heap, where you can actually you can also use heap to implement the priority queue. Remember?
Oh,
Yes or
now I
no?
remember.
Okay, good. All right. So today we're going to be looking at another tree structure, but you will see that the property is a little bit different than the one that we look into heap. Okay, so just a little bit of refresher, so that you don't get confused. Okay, between BST and heap, is that in heap, remember we have the max heap, the min heap, and the property is that the parent will always, if it is a max hit, the parent will always be bigger than the child. Okay, so later on we're going to see that BST have a different property, even though it is still using a binary tree, but the property is a little bit different, and it does not have to be a nearly complete binary tree. Okay, remember for heap you need to fill up the tree from left to right, But for binary search tree, you don't have to do it. The tree does not have to look like it is nearly complete or a complete binary tree. Okay. All right. So the running time complexity for BST is almost the same like the heap, which is the height of the tree, which is order of log n. Okay. So and then if like let's say like you somehow unfortunately get some kind of like a BST that looks like this, right? Therefore, the running time complexity for the operation may take order of n. Okay. All right. Okay. So for the BST, we're going to be using binary tree as well. Okay. So again, as I mentioned, for the heap, you need to have the nearly complete binary tree. Like basically you fill up from left to right. But for binary search tree, you can have a binary tree that looks like this. So this is a valid binary search tree. Okay, so this is heap, which is a nearly or complete binary tree. But for BST, it is just like any binary tree. It can be a BST. Okay. And then for BST, you can represent the tree using data structure such as linked list or array. Okay, and then in addition to a key and satellite data, so basically you will have left, right, and parent. Okay, whereby like you have basically you will have the parent, the left, and the right. Okay. So for BST, if child or parent is missing, okay, it will contain nil, the value nil. All right. And the only node that does not have a parent would be the root node. Okay. So the root node does not have any parent. Okay. All right. So basically, that is the structure of a binary search tree. So please distinguish between heap. Don't get confused between heap and BST. Okay. All right. So for binary search tree, okay, the case in binary search tree, as I mentioned, there is certain property that you need to make sure, just like heap. Okay. But for binary search tree, the property is that if you have a node in the left subtree of X, then Y is always going to be less or equals to X. Okay. And if Y is on the right subtree of X, then Y is going to be bigger or equals than X. With that said, let's say, for example, we have this BST, right? So let's say, for example, we have this value. Anything that is on the no, I'm not doing this one. Okay, so anything that is on this side of the tree, this is the left side, right? This is the left side of the tree. All the element, okay, inside this tree is going to be lesser than 6. Okay, that is the property. And all the element on the right side of the tree would be bigger than 6. Okay, that goes for any subtree below it. So if let's say, for example, I want to see this node. So we can say that, maybe I'll change the color of this, maybe I'll use green. Okay, so whatever element inside this left subtree would be smaller than 5, and any element that is on the right side of 5 would be bigger than 5 or equals to 5. Okay, same goes for this one. So if let's say, for example, I want to know I want to see node 7, whichever that is on the right side is bigger than 7. And since this one does not have, in case there is element inside here, whatever that is inside this side of the tree would be smaller than 7. But since this one is 6, 7, so I'm not sure, maybe 6.5. I don't know. Okay, so it would be smaller. So basically, the property for BST is like this. All right, so whatever in the left side of the node would be smaller, and whatever element that is on the right side would be bigger than the node. All right. And then if you remember the tutorial that we do, so as you can see, these two trees have the same element, but the tree looks different. Okay. So basically, this is a BST of height 2, and this is a BST of height 1, 2, 0, 1, 2, 3, 4. Okay, so this one is BST of height 2, and this is BST of height is equals to 4. If you still remember the tutorial that we do, even though they contain the same keys. Okay, so again, later on, you will see that the reason for this is that when it depends on how the key arrives and you insert the key into the BST. All right. Okay. Are you good so far regarding the BST and its properties? Yeah. Any question?
Okay.
All right. So first, let's look at the how do you call that? The visiting operation that you can do for BST. There are three ways that you can actually traverse the tree. Okay, there are this in order. We have the in order tree walk. Okay, and we also have the pre-order tree walk and post-order tree walk. Okay, so so for sorry, okay, all right. So if let's say we have okay, so let's say we have this BST. Okay, so let's say for example you want to print all the keys inside your BST. You can use a simple recursive algorithm in order tree walk, pre-order tree walk, or the post-order tree walk. But the difference is that for the in-order tree walk, if you use the in-order tree walk algorithm to print out the element inside the BST, you are going to get an increasing order sequence, okay, out of the element. For the pre-order tree walk and the post-order tree walk, it's just that you're using it to traverse the tree, okay? So for the in-order tree walk, the algorithm is that you will visit, okay? First, you're going to visit the left, and then you're going to print the key, and then you're going to call, and then you're going to sort of like recursively go to the left, print the keys, and then move up. We're going to be looking at it later, but basically this will be the algorithm, okay? And this algorithm will be running order of n time, because basically in order for you to print all the elements inside the tree, you will have to print n number of times. So therefore, for the in order tree walk, the running time complexity will be order of n time. Okay, so let's see how do we traverse the tree in a form of in order, whereby if we use this traversal, we can actually extract the element in an increasing order. Okay. So please look at this table, this BST. So let's just check that on the left subtree, all the element is smaller than 15. All this element is smaller than 6. All this element is bigger than 6. We have 3. 2 is smaller than 3. 4 is bigger than 3. 7, 13 and 9 is bigger than 7. 13, 9 is smaller than 13. Okay, so the BST hold. And then same goes for here, 18, 17 is smaller than 18, and 20 is bigger than 18. Okay, so this is a BST. So let's try and do the in order traversal. Okay, so the trick is that for the in order, for you to be to follow this a little bit easier. Okay, we can say that in order, the sequence of print is that you're gonna print the left first, and then you're gonna print the root, and then you're gonna print the right. Okay, we're just gonna keep it that way. So so what we're gonna do is that we're gonna start from the root. Okay, so we're gonna print the left first. So we're gonna traverse to the leftmost node. So we're gonna traverse down. We still have the left node. We travel down. We still have the left node, and then we travel down. We do not have a left node. Okay, left node. We do not have a left node. So we're gonna print 2. So we're gonna print 2, right? So we print 2, and then after that, we need to go back to the root. And then we're going to print the root, which is 3. And then we're going to go to the right. And then we're going to, but the right one, if like, let's say there's a left, like let's say if there's a left, you need to go to the left. Okay. So, but in this case, there's no left. So we're going to print out 4. Right. And then there's no right. And then we're going to go up. Right. And 3, we have print out 3. And then we're going to move up. So left, we're going to print 6. We're going to print the root. And then we're going to move to the leftmost. Okay, you're going to go to the left. And then for this one, there's no left, right? So we're going to print 7. Okay, so you're going to print 7. And then you're going to move to the right. And then we're going to move to the left first. Okay, to the left. And then since 13 got a left, so we're going to print 9 first. And then we're going to print the root, which is 13. But there's no left. So we're going to move up. Right? We have print 7. We have print 6. And then we're going to go to 15. So 15 we haven't print. We're going to print 15. And then we're going to go to the right. Okay? To the right, 18, we're going to see the left first. So 18 still got a left child. So we're going to go to the left. 17, there's no left child. So we're going to print 17. And then we're going to print the root, which is 18. And then we're going to go to the right. And since 20 does not have a left child, so we're going to straight away print 20. Okay, so that is the sequence of an in order 3 walk. So if you see the way that it prints out using the in order 3 walk, you are going to get an increasing order sequence element. So 2, 3, 4, 6, 7, 9, 13, 15, 17, 18, 20. Okay, so when you do the in order 3 walk, you are going to get a sorted sequence, okay, out of the element inside the BST. So are you good so far? So basically, the thing is that you always check for if, like, let's say they don't have a left child. So if they have, you need to keep traversing down the left and then print the left first, and then you're going to print the root, and then you're going to go to the right. You still need to check whether the each node, whenever you visit each node, you need to check whether it has a left or not. Okay, so if there is, you need to traverse down until the end of the leftmost leaf, and then you're going to print it, and then you're going to do keep recursing back the step, which is printing left, root, and right. Okay, so that is the in order 3 walk. So I know it's a little bit confusing, but maybe you can try it yourself. Okay. So for the pre-order, the sequence is a little bit different. Okay. So for the pre-order, the traversal will have to start from, you will print the root first. Okay. And then you're going to print the left. And then after that, you print the right. Okay, so there's a different for the in order, you print the left first, and then you print the root, and then you print the right. For the pre-order, you print the root first, and then the left and the right. Okay, so for example, if let's say we start from 15, so we're gonna print 15 first. So we're gonna print 15, right? And we're gonna go left, and we're gonna print the root first. So we're gonna print 6, right? We're gonna go to the left, and then we're gonna print 3, and then we're gonna go down, and we're gonna print 2, and then we're gonna go to the left, but we don't have a left, and then we also do not have a right, and then we're gonna go up. But since we have print this root, we're gonna go down, and then we're gonna print 4. Okay, and then we're gonna print the left, but there's no left, and then we're gonna print right, there's no right, and then we're just gonna go back up. So we have print 3, we have print 6. So 6, we're gonna go to the right. Okay, so now we're gonna go to the right. We're gonna print 7, and then there's no left. So we're gonna go to the right. We're gonna print 13, and then we're gonna go to the left. We're gonna go to the left, which is we're gonna print 9. 9, there's no left, there's no right, and we're gonna go back to 13. And 13, we have print 13, right? So 13 have no right, so we're gonna go up 7. We have print 7 already. We're gonna go up to 6. 6 has been printed as well, and then we're gonna go up to 15. 15 has been printed as well, and then we're gonna go to the left side. Okay, we're gonna print 18, and then we're gonna go to the left, and we're gonna print 17. We move up, we have printed the note, and we're gonna go print the last one, which is 20. Okay, so this is the pre-order tree walk, whereby you can visit all the elements inside the BST using the pre-order tree walk by visiting root, left, and right. Okay, so the sequence is going to be different. Okay, that you're going to get. So basically, this is just for you to like traverse the BST. Another way of you doing the traversal is the post order. Okay, so for the post order, the order of printing would be, you print the left first, and then you print the right, and then last you print the root. Okay, so this is the sequence for the post order. So let's try on this one. Okay, how do we do the post order tree walk? Okay, so first we're going to go left. Okay, so we're going to go left, we're going to go left, and we're going to go left, and we have no more left. So we're going to print left. So we're going to get 2. And then we're going to go up. This is the root. And then we're going to go to the right first. And then we're going to print 4. And then 4, once we print 4, and then we're going to go back to the root. And we're going to print 3. Okay. And then we're going to go up. This is the root. You still have the right. So we're going to traverse to the right first. Okay. And then we have no. And then we need to go to the left, and we have no left. And then we will basically, we are going back to 7, and there's a right. So we're going to go to 13. Okay. So for 13, is there a left? There's a left. So we're going to go to 9 first. And then 9 have no left. We're going to print 9. Okay. And then 9 is going to go back to the root. And then since 13 has no right, so it is going to print the root 13. Okay. So since this one coming up from the right, and then it's going back to the root. So now it's going to be printing 7, and then 7 is going to go up to 6, and it's going to be printing the root, which is 6. Okay, and then from 6 is going to go to the root, and since 15 have a right side, it is going to go to the right first. Okay, and then since 18 as well still have a left, so 18 we're going to go down to 17. So 17 there's no left, so, and then 17 have also have no right, so we're going to print 17 next, and then 17 going to go up to 18, and then since 18 have a right child, it's going to go to the right child. 20 does not have a left child as well as the right child, so it's going to be printing the root, which is 20. So 20 is going, after 20 is going to go back to the root and going to print 20, and then it's going to be printing 18, and then 18 is going to go back to the root, and finally it will be printing 15. Okay, so do you see the difference between each of these? The way it travels, the way it prints, basically it prints, the sequence of printing is different from the pre-order and the post-order. And for the pre and post order, the sequence basically the element that you traverse, it will not give you the sorted order. Okay, so if you want to, like, let's say for example, extract it in a sorted order, you need to use the in order tree walk. Okay, all right, so are you good so far? Do you see it?
Yeah. So if I'm getting this right, in order they print. In order. Pre-order. They print every time. They print out every time they pass a node once. So they if you look at the pre-order example, they first start print out the root node and then goes left and then prints out the node it passed by, and then every time it passes by a node that it hasn't printed yet, it prints it.
Kinda. So basically, because since the pre-order, it prints out the root first, because you always reach the root first. That's why it gives you the sense of the feeling that you are printing on whichever node that you travel on.
And then post-order
but yeah, kinda.
And then post-order is print the children's first and then the parent.
Yeah.
Okay.
Yeah. Okay. But all of them will print each element once. Okay. Each node once, not element. Okay. All right. So the analysis, we're going to be looking at the in-order tree walk. So basically, for this operation, the running time complexity will be taking order of n times, because of course you need to traverse each node, and each node correspond to the size of the element. So therefore, the running time complexity for in-order tree walk takes order of n time. Okay. All right. So how are you like want to query a BST? Okay. So normally when you are using BST, you want to search for a key, right? Just like when you use hash, and so you want to search for a key. Okay. So and then in BST is other than you doing search, you can also find what is the minimum, maximum, successor, as well as the predecessor, okay, of a node or of an element from the BST. All right. So let's look at the first operation, whereby if let's say you want to search a certain key. Okay. So let's say for example, you need to find a key K. All right. And then basically, if you use the tree search algorithm, will return you on which node that key K exists, or else it will return nil. Okay, meaning the key has not been found in the tree. Okay. So what are you going to? So basically, the algorithm here as you can see. Okay, so you check whether if x is equal to nil or the k is equals to x key, and then you're going to return x. So basically, the x is actually at the root. Okay, and then if you look at line 3, we check. Okay, if k is less than x key, all right, and then you're going to go search the left, else you're going to search the right. Do you know why? Do you know why we do this, class? Why one, when we check if the k is lesser than x key, we go search the left side, else
Because
we search that side.
because the left side is where the smaller value than the root node is.
Okay. Yep, that's right. So basically, it corresponds to the property of the BST, which is whatever element that is on the left subtree is smaller, and whatever on the right subtree is larger than the root node. Okay, so therefore, the searching normally. So if, like, let's say, you can imagine if you have a tree, you sort of like eliminate half of the tree. Okay, so in a sense, it's either you move to the left or to the right. So in that case, what is the running time complexity for doing search in the BST class? What is the running time complexity for doing search in BST?
Log n?
Which is the height of the tree, right?
Yeah.
So the running time complexity for this one, it will be order of log n. Okay, so basically all you have to do is just to traverse down, or you're almost like traversing down the tree. Okay, so because since you either go to the left or go to the right. Okay, so you'll be traversing either this way, or you're traversing this way, or you're traversing this way. Okay, so basically the running time complexity, the big O, for this algorithm would be order of log n. Right? Right. So how about the maximum and minimum? What is the maximum and minimum? For the BST, where can you find the maximum and the minimum? If you think about the properties of the BST.
Rightmost, leftmost.
Yep, you can say that the rightmost, sorry, the leftmost would be the minimum, and the rightmost element, basically, if you have a tree, the rightmost node would be the maximum, and the leftmost leaf would be the minimum. Okay, so if, like, let's say, for example, you have this tree. Sorry, we have this tree. Okay, so the minimum is going to be the leftmost, which is this one. The maximum is going to be the rightmost, which is this one, the rightmost node. Okay, so that would be the maximum of the left subtree. This is the left subtree, so we want to find the rightmost, and sorry, in the left subtree you want to find the leftmost, and on the right subtree you want to find the rightmost node. Okay, so in this case, this element is going to be the maximum, and this one is going to be the minimum. This is going to be the maximum. All right, and again, the running time complexity for finding the minimum and the maximum, it would be the height of the tree, which is order of h or log n. Okay. All right. Okay, so basically, if you implement the BST, to find the minimum, you just follow the left child pointers until you encounter a nil. Same goes for maximum. for maximum, which is the rightmost, okay, until the right child pointer until you encounter a nil, okay. And then sorry, order of n for maximum and minimum, are you sure? Unless your tree is unless your tree is like this, then of course the runtime capacity will be order of n. If your BST is like this, then all you have to do is just to traverse down the height of the tree, not order of n.
So it's also log n?
Yeah, it's also log n. Yeah. Okay. Gori, is that do you get what I mean? The length of the tree is not n. If your tree, the height of the tree is n, therefore you are having this tree, not this tree. Gori, do you get it? It is not n. Right? Okay. So for this one, the tree maximum is symmetric to the finding the tree minimum. Okay, so basically, the right side and then the other one is on the left side. Okay. All right. And then there is an operation for finding a successor and predecessor. Okay. So let's say, for example, you have a node and you want to find what is the next biggest and what is the next smallest. Naively, what you would do is that you are going to arrange, if like, let's say you're using a normal array, basically you need to have a sorted order, and then you need to find, if you want to find a predecessor, so if like, let's say you have this array, and we have, these are basically sorted, and if like, let's say we have an element here, so in order for us to know what is the predecessor, we just look at the index before. So this is the predecessor, and then this one would be the successor. How to spell successor? Okay, so basically, if it is an array, the predecessor would be the element before, the successor would be the element after. Okay, so basically, naively, in order for you to do what is the next biggest number, is that you need to have a sorted list and find out what is the one after what or before. Okay, in a BST, there is since you know that since the way that it is being arranged, you do not have to sort of like do the sorting first before you find what is the predecessor and what is the successor. Okay, all you have to do is just you need to traverse down the length of the tree. Okay, because if you notice, okay, when you do the in order tree walk, you can actually get that sorted order while you are doing the in order tree walk, right? So let's say, for example, okay, so here we assume that all the keys are distinct, and we can say that the successor of node X is the node with the smallest key greater than X. The predecessor is when node X, node with the greatest key smaller than X. Okay. So for the BST, we can actually do this, okay, without doing the comparison. Okay, without comparing, like whether it is actually bigger or smaller, all right, than the key that we wanna that we have. Okay, so if we look here, all right, this is the pseudocode for finding the tree successor. So how are we going to find the predecessor is that Oh, my nose is a little bit blocked. Okay, so if like let's say maybe we're just gonna look at an example. It will be much easier. Okay, so for a successor, basically I can summarize. If you want to find what is a successor, there are two things that you need to consider. Okay, so if like let's say a node, okay, a node, if like let's say you want to find what is the successor of this node, okay, if this node have a right subtree, you can just find what is the minimum inside this right subtree. Okay, so that is how you find what is the successor of this node. If it has the right subtree, you find the minimum inside this right subtree. Okay, if let's say for example, okay, so I think I better like if so for the first case, if there is if right, you have right, and then find minimum in right subtree. Okay, so that is if there is a right subtree. So if like let's say for example you have a tree, I hope I make sense. So if like let's say we have a tree that looks like this, let's say for example, okay, and then we want to find what is the successor for this node. Okay, so since this one we do not have a right child we do not have, what we're going to do is we need to find what is the nearest ancestor. Okay, nearest ancestor whereby this node came from the left subtree, is within the left subtree, is in the left subtree. Okay, so what it means is that, so since this one there is no right subtree, okay, you need to traverse up and check what is the nearest ancestor whereby this node belongs to the left subtree. All right, so in this case we traverse up, we look at this parent. Okay, but this node belongs to the right subtree, so this one is not the successor. So you need to go up and look at this node. So this node, it looks like this node belongs to the left subtree of this node. Therefore, the successor is this one. This is the successor. Do you get what I mean? Okay, so basically I can generalize the step for finding the successor for a node is that if there is a right subtree, just find the minimum. If there is no right, you need to find ancestor that whereby the node belongs to the left subtree of that node, the ancestor node. Do you get it, class? Hopefully. Maybe we can try an example later, okay, in the next slide. So for the predecessor, meanings we want to find the one before. So it is symmetric as well. So if like let's say for example, if you want to find the successor, we find the right subtree minimum. So for the predecessor, we're going to find the left subtree maximum, and we're going to find the ancestor whereby the whereby the node belongs to the right subtree of the ancestor. Okay, so it's like symmetry. So you just change. Okay. All right, so that is for the successor and predecessor. Okay, so let's just quickly look into this example. Okay, so like, let's say for example, if you want to search key 13, we're going to traverse the tree as first, we're going to start at the root. Okay, we're going to start at the root. 13 is less than 15, it's going to go to the left. 13 is bigger than 6, it's going to go to the right. 13 is bigger than 7, and then it's going to go to the right, and then you find 13. Okay, so that is how you do search in a BST. And then the minimum of, what is the minimum for this tree? Basically, it will be the leftmost. Yes, it will be the leftmost. So basically two. So we need to traverse to the leftmost leaf until we encounter a nail. So therefore, our minimum is 2. How about maximum? Our maximum will be we need to traverse to the rightmost until we encounter a nail. So our maximum would be 20. Right? What is the successor for node 15? So node 15, if you want to find the successor, we need to go, there's a right child. So the right, there's a right child. So we need to find the minimum inside the right sub tree. So in this case, the minimum of this, subtree would be the leftmost, which is 17, right? So this would be the successor for 15. And how about the successor for 13? Since 13, here, there is no right subtree. Remember, we need to find, it will be 15. We need to find where the node belongs to the left subtree of the node. So in this case, it would be, so this one is right, and then go out. This one is still like belongs to the right, and we go out, and now 13 belongs to the left subtree, and therefore the successor of 13 is 15. Okay, so are you good so far for all these operation, finding search, maximum, minimum, successor, and predecessor? Yeah, class?
So predecessor is the rightmost on the left side, and then successor is the leftmost on the right side. Can you repeat it?
If there is there are two condition, okay, whereby when you want to find the successor or the predecessor. Okay, so first you need to check whether, if like let's say you want to find the successor, you need to make sure that you have the right child. If you have the right child, meaning you have a subtree there. So if you have the right child, you find what is the minimum inside that left subtree, that right subtree, sorry. Okay, and if you do not have, if like let's say the node do not have the right child, you need to find the left, that node needs to belong to the left subtree of the ancestor. Okay, so that is the for the successor. For the predecessor, you change it. So it's it should be find the maximum in the left subtree, and the node has to be on the right subtree of the ancestor. Okay. All right. So we have insertion and deletion. I think the deletion is a little bit what you need to. Do you want to take a break for a while, like 5 minutes, class? I think we can end the class quite early today, but do you want to take a break for a while? Yeah, 5 minutes.
Okay.
Okay. All right. Let's continue into the last two operation of a BST, which is the insertion and the deletion. Okay. So, for the BST insertion, it is very easy. Okay. But for the deletion, you need to consider a lot of condition. Okay. So we're going to be looking at these two next. Okay. So, so basically when same like when we do if you remember when we look into heap where whenever we insert or we deleted an element or a node, okay, we need to make sure that the property hold. Same goes for BST. Whenever we do our insert or delete, you need to make sure that the binary search tree property continues to hold. Okay. So as I mentioned, inserting is straightforward, but deletion is a little bit, it takes a few steps for you to actually delete a node, okay, which we're going to be seeing later. All right. So for the insertion, let's say for example, you have a value V coming in, okay, and you want to insert that value into the binary search tree. You can use this tree insert procedure. Okay, so what it does is that it is going to find what is the appropriate place to put the new key into the BST. All right. So this is the steps. Okay. Maybe we'll just look straight away to the example. So let's say, for example, we have these three, okay, and we want to insert 13 into the BST. So what we are going to do is that we are going to find where we want to insert key 13. All right. So how we're going to do is that we're going to we're going to start at the root, okay, and then we're going to see if 13 is bigger than 12. Yes. Therefore, we need to move to the right. Okay. Is 13 bigger than 18? No. So it has to move to the left. Okay. So is 13 smaller than 15? Yes. And 15 said, and since 15 the left is nil, we can append 13 here. Okay. So insertion is very easy. Okay, all you have to do is just compare and then find until you find a node where the child is nil. Okay, the left child or the right child is nil. Okay, depending on the value that you want to insert. So inserting element into the BST is very straightforward. Okay, so therefore that's why when you want to use the BST, okay, you need to make sure, even though you don't know what is the size of the element, you need to make sure that the distribution of input or the element that you want to put into the BST is random. Okay, and there is no sequence whatsoever inside the input set. Okay, because if you have some sort of like ordered pattern, okay, ordered sequence inside your input element, you are not going to get a balanced BST. Not necessarily like a balance, but but we want to make sure that our BST does not give like this linear looking tree. Okay, so if it is sorted somehow, if the distribution, you have that sorted pattern, okay, inside within your input, you're probably going to get something like this, okay, which is not good. So therefore, the Renington complexity is not going to be log n, but it will be order of n, okay. And therefore, if like let's say, therefore you need to assume that the distribution of your input is random and there is no sequence, okay. All right. And then we are going to look at how are we going to do the deletion, okay. So the problem with deletion in BST is we need to somehow plan properly on how are you going to replace the deleted nodes, okay. So if we look at this example, okay, so let's say for example, is this a good example that I want to delete? Okay lah, maybe like let's say I want to delete node 12, the root node. Okay, I want to delete this one. I cannot simply delete this and replace with 5 or 18, right? Because it's not possible, since like if I put 5 as the root node, and then somehow this 9 and 18 is like on the right side. Same goes if I replace 18, and then this one, how am I going to how do you say, combine between the two sub-tree, right? So therefore, for the deletion of BST, there are some steps that you need to follow, okay, before you can actually delete a node that have particularly 2 children, okay. All right. So there are three conditions when you want to delete a node in BST. So for the first condition, if the node that you want to delete, or the node Z that you want to delete, have no children, then all you have to do is just remove the node. Okay, so meaning in a sense, if like let's say you want to delete 2, okay, since 2 have no children, you can just simply delete 2. All you have to do is just remove the pointer, okay. So basically what he's saying, all nodes that are leaf nodes, all you have to do is just cut the pointer to the node, and then just take it out from the memory, okay. So that is how you delete node with no children, okay. So that is the easiest way for you to delete that is the easiest node in BST that you can that you can delete, okay. That is for the first deletion, okay. So if you have a node that have no children, you can just take it out from the BST. So meaning in a sense, after you take it off, let's say for example, I want to delete 2. So the next 3 will be this one, excluding the 2. Okay. So this will be the new 3 after you delete 2. Okay. And then for the second condition, if like let's say it has 1 child, okay, what are we going to do is that we are going to elevate the child to take the Z position in the tree by modifying Z's parent to replace the Z by Z's child. Okay, so let's look at the example. Okay, so let's say for example, we have node with 1 child. Okay, so like let's say we want to delete 6. Okay, we want to delete 6. Sorry, 6 have 2. Okay, maybe 7 lah. Wait, how many child? Okay, so let's say for example, we want to delete 7. Okay, and 7 only have 1 child, which is the left child. Sorry, the right child. So all you have to do, not delete 7. Okay, so So you want to delete 7, and 7 only have one child. So all you have to do is that 6 will straight away, 13 will straight away replace 7, and now 13 will be on the on the right side of 6. Okay, the right subtree of 6. You just take it off and just uh, connect to its child. Okay. By doing this, you are still going to preserve the BST property, which is the left side is smaller and the right side is bigger. The left subtree is smaller and the right subtree is bigger. Okay, so for node with one child, again, it's quite easy to do, which is all you have to do is just that if like let's say 7 only have one child, you just replace 7 with 13. So therefore, the new subtree will look like this: 6, 3, and so on and so forth. And then you're going to get 13 and 9. Okay. So if we check, this right subtree still hold the property, which is all the element inside the right subtree is bigger than 6. Okay. Is there any more? Maybe I can give one more example maybe. Okay, so maybe let's say for example I add one child here. Let's say maybe we put 16 here. Okay, so if like let's say I want to delete 17. I want to delete 17, and all I have to do, since 17 only have one child, all I have to do is just I connect 18 with 16, and the new subtree is we're gonna have 15, 18. Since we take off 17, we're gonna get 16 and 20. So therefore the property still hold. So in order for you to delete a node with one child, all you have to do is just replace the node with the child node. Okay, so that is for deleting node with one child. Okay, so the one that is the trickiest is that if like let's say the node has 2 children. Okay, this is when we need to find what is the successor, so that you can use the successor to replace the node, and then somehow reduce reduce whatever deletion that you need to do into either case 1 or case 2. Okay, so let's say for example so let's say for example we want to delete let's say we want to delete 6. Yeah, we want to delete 6. I think 6 would be, we want to delete 6. Okay, so 6 have 2 children, and now we want to find out how are we going to delete 6. Okay, so what are we going to do? If we have two children, okay, if we have 2 children, we need to find what is the successor, and then we're going to replace the node with the successor, and then we're going to keep the rest of the tree as such. Okay, so in this case, to find the successor of 6, remember, we need to look at the right subtree. Okay, the right subtree, and find what is the minimum, what is the mean, right, in the right subtree, in order to find what is the successor for this one. So in this case, what is the mean for the right subtree? It would be the leftmost element in the subtree. What is the leftmost node in the subtree? Let's say this is the root. What is the leftmost? No, 9 is not the leftmost. Because
7.
in
7
order
because
you
7 there's no left.
Yeah, so therefore 7 is the leftmost, because if you say 9 is on the right sub 3. Okay, you need to find the leftmost in the left sub 3. Okay, so in this case, this one, the minimum would be 7, and therefore 7 is going to replace 6. Okay, so therefore 7 is going to replace 6. So now the new sub 3 is going to look like 15, 7, 13, and 9. Okay, and then 7, we're going to get 3, and so on and so forth. All right, so that is how you're going to do the replacement. Okay, you need to find what is the successor of the node, and then you're going to replace it. Okay, all right. So did I miss anything? So both left and right child, we find what is the successor. Deletion of 15. Okay, 1 second. Right sub 3 that has which lies in the Z right sub 3, which has no left child. And you want to splice the Y out of the current location and press Z in the
Doctor.
Hmm.
So if the successor, yeah. So if the successor also has two children, then the process repeats itself until everything is sorted out, or
how would you get the successor with a child, because it's the minimum of the right sub 3, so it has to be the leaf,
Oh,
the
yeah.
last, right?
Yeah, never mind.
So at least it will have, at most it will have only one child, right?
Okay.
Yeah.
Okay.
Mm. Okay, so if Y lies within the right sub 3 and it's not the right child, in this case we replace by its own right child. Okay, so if like let's say we want to delete 15, right? So if you want to delete 15, 15 have no, I think Gori was asking if like let's say we want to delete 15. Okay, so let's say we want to delete 15, we're going to look at the right child and find the minimum. What is the minimum in this case? It would be 17, right? And then what you're going to do is that you're going to put 17 up here. So now, so 15, you're going to replace 15 with 17, right? And then just keep the rest of it as such. So basically, you just you basically you reduce it to case one. Case one, whereby 17 is at the leaf. So all you have to do is just take out this note. Sorry, just take out that note. But I'm putting this on do not disturb. Okay, so you replace this note with 17, and then you just delete this one and you keep the rest of the child intact. Is that okay, Gori? This is the what going to, sorry. Oh, Okay, class? Do you get how do you delete this one? So basically what happened in here, the one that we do the first one, is that we find the minimum and then we replace it to 7. Okay. And then since 7 have one child, okay, since it's like we are deleting 7, since 7 have only one child, all you have to do is just you connect this node to 13. That is what we do actually. Okay, same goes for this one. You move it to 17 and then you delete this node. And since this node is at the leaf node, all you have to do is just take out this leaf node. You delete that node. It's like you are reducing. You find what is the node that you want to replace. Okay, the node that you want to replace, the one that is being deleted, which is you find the successor of the node, and then you replace the node with that element, and then after that, so basically you reduce it to either case 1 or case 2. Is that alright, class? You replace 7
Yes.
and then you take it out. Yeah. It's just like you delete. So basically now, if you already replace, you put 7 here, you need to take out this one, right? So since this one only have one child, so all you have to do is just connect this node to this node. Same goes for this one. So you find what is the minimum in the right subtree. You move it up. And then since this one is the leaf node, all you have to do is just take out take it out from the tree. Is that okay, class? That is what happened when you do the deletion. Is that okay?
Yes.
Yeah. All right. Okay. So basically, that covers all the 3 condition. For the deletion. So basically, when you find the element that you want to replace, and then you will do the transplant. Okay. So basically, uh, uh, um, uh, um, you have this subroutine to do the that replace the subtree as a child of its parent. So when you when you find the element that you want to replace, and then you need to do the transplant, basically just to connect back the disconnected subtree. Okay. All right. And then you delete. So basically you delete just like how you delete the element. Okay. All right. So again, the running time complexity for deletion is the height of the tree. Okay, so basically all you have to do is, since you need to do somehow find the what is the tree minimum and so on and so forth. So the running time complexity for deleting a tree is order of log n. Okay. All right. So next lecture, next week we're going to be looking at greedy algorithm. I hope I can finish the lecture in 1 hour because you're going to have your midsem after that. Okay. If you see the slide, you also see like data structure, disjoint set. So this is actually an additional thing that talks about tree. Okay, but I think this one is more like a graph. They don't really like for the disjointed set. I think that one is more like a graph rather than a tree. But for the Fibonacci heap, that one is a tree. Okay, so maybe you can, if you would like to find out more about the Fibonacci heap, you can have a look. Okay, it's just that I think it's better not to cover it officially as a lecture. Okay, and I just found out that this week Thursday is public holiday, right, class?
Yeah.
So I had a feeling that we need to find one day where we can cover the tutorial. Is it possible? The tutorial? Do you have any like 1 hour slot that we can do our tutorial for tutorial 1, 2, 3? I'm not so sure tutorial 4. whether Dr. Raja did the tutorial with you or not. But for my group, can we try and find one slot? And do you think like you can give me on Friday, like 1 hour on Friday? Is it possible?
Not it's Friday,
What?
not public holiday. Oh,
Is it 2
because
days really?
On Saturday it's Labor Day. So I don't know if they bring it forward or what.
Friday is Labor Day. How come?
Saturday is Labor Day.
So if Saturday is Labor Day, no, I don't think so. Friday is public holiday. I don't think so. Because I have, wait, 30th. I don't know, maybe. It's public holiday. I don't know. Did they bring forward? Because I didn't, my calendar does not say public holiday on the 30th. I'm not so sure. I don't think so because I have a meeting on the 30th. Maybe next week. Some other time next week. Any time. Next week. Can ada tak? Can we do?
Extend class for an hour.
Are you sure? Are you sure?
Yes, but I'm not. No, I'm not sure.
3 hours? Are you sure? Because next week we're gonna have mid-sem 4 to 5. Because we need to cover the tutorial. I totally like I think both of us, like me and Dr. Azrina, we overlooked that this week the tutorial, it's public holiday. So maybe you can sort of like maybe I can create a poll and suggest some time. So in general, when can you give me that 1 hour slot? Can you give me an option through the chat, or maybe so that I can create a poll where we can see where the majority is available for that slot. You can always watch the what, but I need a good number of students to be in the tutorial for the thing to not Tuesday. Yeah, not Tuesday for me as well. I can do Monday, Wednesday, Thursday, Friday. Actually, since you said Tuesday is what? Yeah, I just need 1 hour. Let's just like quickly go through the tutorial. I think we just combine tutorial 1, 2, 3. Friday 3 p.m. next week or this week. I think this week is not public holiday lah. Nobody told me that Friday is public holiday. Or is it I missed the memo? 9 a.m. this week. Okay, some got lab that time. 3 p.m. Okay, I'll keep 3 p.m. Friday. If it is not this week, and we can if not this week, next week. As each student, lab Friday 3. Wow, your class, like until Friday 3 p.m. I remember last time our timetable used to like normally after 2 p.m. Friday, no, you don't, no more classes. Now you guys have classes until Friday evening. Oh my god. Wow, 4 to 5 on Friday. Asynchronous tutorial. How, for this tutorial, how do you want to make it asynchronous? For last week is fine because I asked you to use it as like the time for you to discuss and update in the teams, and I see most of the groups have some update. I still like I have gone through some of your updates, but I'm not some of you I still haven't go be able to finish it. But I'm not so sure how are you going to do asynchronous. I just open the Google Doc and then you will give the answer. Is it, Chenny? Is that what you're suggesting? Can I trust you? We'll look at the document. I can. I mean, if if that can work for you, I'm okay. I can do a face-to-face class, or I can do asynchronous. How? Maybe I will just open a Google Doc, and then all of you will contribute to the answer, and then I will just comment it on the doc, and then I will let you know once I commented. If there's a question there, I will try to answer. Yeah, but you need to be so you prefer the asynchronous way.
I feel like since it's easier to plan it.
If there's no other option, yeah. Unfortunately, we are really. I'm so sorry. I like both of us. We really did notice that this week is a public holiday on Thursday. But I think for this week's tutorial, there should not be too many issues. But maybe we can try and do the asynchronous one first, and then take note of any question that you want to ask, and then just dump it into the Google Docs. And then if there is a need for explanation, either I'll comment it inside the document, or I will have like a quick video just explaining that to you, uh, uh, the issues. Is that okay? Maybe we can do that then,
Okay.
right?
Okay.
Okay. Then I will just open the Google Doc link for tutorial 1, 2. We'll have one, and tutorial 3 will have one Google Doc. And then please, somebody, make sure, I trust you. You're gonna go and look at the document. Like, maybe I'll give it like until next week, maybe Monday, for you to prepare the answer inside the docs. And then on Monday, I'll try and review whatever you have inside the Google Doc. Is that okay? All right, maybe on Thursday, or I don't think you want to work on public holiday. I don't want to work on public holiday. I need to rest my brain as well whenever I can. No, I will still be working during public holiday. Like normally I do. But yeah, so I will open the Google Doc. Then you just put in the answer, and I will communicate to that document. Okay. All right. Okay. So that settles for the tutorial. Any more question before we end the class for today? Question, project in Teams channel, and you are in team group what, John? Team 7. Tutorial? Group 7 tutorial? Group 1. Okay. For those of you who have question, please tag my name, because sometimes because there's too many updates, so I'm not so sure whether it is actually a question, or an update for your group. Okay, so because if you don't tag me, then I will just thought that it would be just your group activity inside your channel. If you want to talk to me, please tag my name, add my name. Okay, please tag me, then I know that it is a question for me. Is that okay? Yeah. So the question is that, do we need to scrap the audio, YouTube, and denoise it? Or VK is slightly noisy, the background noise? Yeah, I don't mind. If you do not need to denoise it, it's fine. As long as you can actually run the algorithm, then it's fine. For the speech recognition part, are we allowed to use our own recordings on the words such as memohon maaf? Yes, you can use your own words as well. explanation of DTW, can use pseudocode for the demonstration. Yep, can. And then use the API to do instead of coding. Yes, from the pseudocode. Yes. No. No. Did I answer your question, John? So the question, do we need to scrap the audio of YouTube video and denoise it? No, as long as you can actually run, as long as you can run the algorithm. You want to use your own recording for the words, for the speech recognition? Yes, you can. Explanation of DTW, if you want to use pseudocode to do it, and for the demonstration is yes as well. So no marks will be deducted. Okay, does that answer your question, John?
Yes, thank you, Doctor. And on the post of the on upside, then I have still have some more.
More question. Oh, okay. Okay. So 1.2, 1.3 different problem. Like we need to calculate the direct distance origin to the hub to destination. What does okay? So now 1.2 and 1.3 is not a different problem. It's just that I think in 1.2 I ask you to plot the map without going through the hub, and I think in 1.3 is when you have to go to the hub, and then define in 4 problem in 1.4 refers to, I don't remember what is 1.4. What is 1.4, John? And then in problem 3, does it mean give probability for every possible route of the package being used, or just the total number of possible route? Okay, so when you talk about the probability, you need to somehow create some kind of calculation where when you create that calculation, it's like you are giving a definition of the probability of someone choosing that company for delivery. Okay, so if like let's say your sentiment analysis, how are you going to summarize from the sentiment analysis, and then what are the, how do you call that, what is that word, the compromise or the, oh my god, what is that word? Somehow it's like I don't remember what is that word, but somehow like you determine what are the compromise between the sentiment percentage or the sentiment score with the distance that you have calculated. Okay, so that is what you mean by the one in problem 3. And then this problem 1.4 means before and after algorithm is applied. So basically you need to plot the one before going through the hub and after going through the hub. Okay, is that okay, John? Problem 1.4. 1.4. Yeah, I think define in 4 is typo. I think it's a typo. This one. It's supposed to be defined in 3. 2 and 3 supposedly. Okay? Alright. Is that okay, John?
Yes, sorry, I accidentally clicked the meeting.
Okay, it's fine. I think it's good for the rest of you as well, because I think these are some of the common questions being asked regarding the project. Okay. So yeah, so for those of you who have questions for me, please tag my name inside the channel, because else I wouldn't know that you have question for me inside the channel. Okay, that's why I didn't answer your question, John. Okay. All right. Any more question? No. In that case, I will see you next week. So the first hour we're gonna do our lecture. Okay. Use GUI to demonstrate the whole project. I don't understand what you mean by GUI. Are you going to have the graphical user interface? Yeah, if you want to develop the graphical user interface as well, it's even better. It will look nice. Okay. All right. Any more questions? So, okay. So in that case, next week, mid-sem, details on spectrum. I think it is 20 question, if I'm not mistaken. Okay, divide and conquer and probabilistic analysis. Okay, 20%, all right, for your mid-sem. It will be online, 1 hour, right? Okay, let me stop recording first. All right, so don't forget to sign your attendance and I'll see you next week. Bye. Assalamualaikum. Thank you.
Take care.
Bye.
Thank you, Doctor.
Thanks, ma'am.